So next one is the continuity equation in 3 dimension. Already we discussed about one-dimensional flow studies, two-dimensional flow studies, and three-dimensional flow studies. So in order to study a three-dimensional flow here, otherwise, in order to derive the continuity equation in 3D, first of all, we have to consider a small fluid element. We have to consider a small three-dimensional fluid element. And the coordinates are x, then here it is y, and here it is z. Okay. And this box represents the fluid element. This box represents fluid element. So along this x direction, fluid come from this direction and leave along this direction. Okay. And along y direction, fluid come in this direction and leave along this direction. And in z direction, fluid come in this direction and leave along this direction. Parameters in a particular direction is a function of other two directions also. I am considering the flow along x direction first. See here, A, B, C, D represents the entry. This A, B, C, D represents the entry. Okay. And this E, F, G, H is the exit along x direction. So some amount of flow come in this direction and some amount of flow go out through this direction. And similarly, some amount of flow come in this direction and flow, go along this direction in the case of Y. And similarly, some amount of flow come in this direction and go out along this direction. Okay. So initially, I am considering the flow in this direction. Okay, A, B, C, D, and also going out through E, F, G, H. Okay. So now fluid element is dx, dy, dz. So here the length of the fluid element is dx. Here this dimension is dy, and here this dimension is dz. So we are considering a fluid element of length, breadth, and height is dx, dy, and dz. Then u, v, and w are the inlet velocity components in x, y, and z direction. So here it is, u is the velocity along this direction, and v is the velocity along this direction, y direction, and w is the component of velocity along z direction, Okay. Now see, the mass of fluid entering in the phase ABCD is equal to rho AV, rho into A into V, that is rho into area ABCD into the velocity in x direction. Okay, that is rho u dy dz. I will show that that is here it is rho into u into what is the area of this phase, that is area of this phase will be dy into dz. That's the area of this phase. Okay, that is why rho into u into dy dz. Then mass of fluid leaving the, not force, mass of the fluid leaving the phase EFGH. Mass of fluid leaving the phase EFGH. Mass of fluid leaving the phase EFGH. Okay. So the amount of flow come in this direction plus or minus something through this direction. Then you see that mathematical expression, that is mass of the fluid leaving the phase EFGH is OU dy dz. It is already there, plus dou by dou x of, that is variation along x direction, dou by dou x of same quantity into dx. This indicates, this mathematical representation indicates the variation of that much quantity along the x direction. Clear? I think it is clear to you. Okay. So whatever the quantity in the inlet side plus some gain or loss, That is the amount of flow which is passing out the exit. Okay, I think it is clear to you. And similarly, so we have to consider in the y direction and we have to consider in the z direction. What about this direction, y direction? The entry is at CD, okay, DCGH. That is the entry. What is there? That is V into velocity. That is rho into V into small v. Rho into V into what is the area of that phase? Area of that phase is dx into dz. Okay. And what will be the exit? What is going exit? Then there will be the quantity here. What is that quantity? That is rho into V into dx into dz plus along this direction. That is dou by dou y of the same quantity. That is rho into V into dx into dz into dy. And what about in the z direction? Rho into W into then area at that direction plus dou by dou z of those things into dz. Okay, that is in the case of z direction. You see the figure in the z direction. So we are having in the z direction rho into W into dx into dy plus dou by dou z of those things. What are going rho into W into dx into dz? Okay, into dz. That's the concept in the case of this direction. So you studied the flow along this direction, you studied the flow along this direction, and you studied the flow along this direction. Once again, you see, so the mass of fluid entering the phase ABCD, mass of fluid leaving the phase EFGH. Okay. Then the gain of mass in x direction is the exit quantity minus inlet quantity. Exit quantity minus inlet quantity. So this term and this term get cancelled. What is the remaining one? Dou by dou x of OU dy dz dx, which means that dou by dou x of OU dx dy dz. Okay, rearrange it. Similarly, the net gain of mass in y direction is dou by dou y of OV into dx dy dz. Similarly, the net gain of mass in z direction, what is that? Dou by dou z of O into W into dx dy dz. Okay. Therefore, the net gain of mass is equal to dou by dou x of OU plus dou by dou y of OV plus dou by dou z of OW. That into dx dy dz. That is the net gain of mass. Okay. And since there is no accumulation of mass, as per the law of conservation of mass, the equation C6, that is this equation. The equation C6 becomes dou by dou x of that quantity plus dou by dou y of dou v plus dou by dou z of OW dx dy dz is equal to 0. Okay, and in this expression, this dx, dy, dz are constants. Therefore, they may not be 0. But something into 0 will be 0. That is why the remaining term, this term, that is dou by dou x of OU plus dou by dou y of OV plus dou by dou z of OW is equal to 0. Therefore, we can modify this expression as dou by dou x of u plus dou by dou y of v plus dou by dou z of w is equal to 0. Otherwise, dou u by dou x plus dou v by dou y plus dou w by dou z is equal to 0. That is, if the fluid is incompressible, rho is equal to 0. Rho is equal to a constant. Okay, that you have to correct it. If the fluid is incompressible, rho is equal to c, is a constant. Hence the equation becomes dou u by dou x plus dou v by dou y plus dou w by dou z is equal to 0. And this is the continuity equation in 3D. And it's a in the case of 2 dimension, any one of the parameter will be 0. Therefore, dou u by dou x plus dou w by dou z is equal to 0. Otherwise, dou v by dou y plus dou w by dou z is 0. Otherwise, dou u by dou x plus dou w by dou z is equal to 0. That you can modify according to the parameters you are selecting for the fluid flow studies. Okay. There is a correction for the last equation, that is dou u by dou x plus dou v by dou y is equal to 0. That you have to correct it. Okay.